Hello data scientist, welcome to Skillcate. In this course, we will build a sentiment classification model using neural networks. We will use the popular IMDb movie reviews dataset and train three separate neural networks, namely a simple neural net, a convolutional neural net or CNN, and lastly a long short-term memory or LSTM neural net. LSTM networks are actually considered to be quite suitable for handling NLP problems, and by the end of this video you will understand why. Just to give you a quick glimpse, the sentiment classification LSTM model we shall be training as part of this tutorial is so good that it not only predicts the user sentiment as positive negative, it also does a fabulous job in predicting the IMDb rating itself corresponding to these reviews with quite good accuracy, as you can see here. During the course of the next 20 minutes or so, we shall discuss the mighty word embeddings, which is a very powerful feature extraction technique, intuition on various neural network approaches, the concept of overfitting that happens when a model memorizes training data rather than understanding general distribution, and of course our high-level solution architecture for training our sentiment classification model. So without further ado, let's get started. For introductions, we are Skillcate, and we're on a mission to bring you application-based machine learning education. We launch new machine learning projects every week, so make sure to subscribe to our channel and also hit that bell icon so you get notified of all our new ML projects. Really seek your support here, guys, as this keeps us motivated and helps us in reaching out to more learners like you. And yes, let's talk machine learning. People, in case you need any ML project related help or want to discuss your crazy ideas, you can go ahead and book a free one-on-one online session with us by visiting our website skillcate.com and filling out this one-on-one mentoring session registration form. Or you may write to us over email, WhatsApp as well. Alright, coming to the topic of discussion for today, which is sentiment classification using neural networks. Let me start off with our solution architecture and a brief on the basics. This is our high-level solution architecture. As a first step here, we are using the IMDb movie reviews dataset that has 50,000 reviews along with positive, negative sentiment labels. This is how our dataset looks like. We have these movie reviews in the first column mapped with their sentiment labels, positive, negative. This bar chart depicts the distribution of our data across sentiment labels, and it seemed to be fairly uniform. Okay, back to the architecture. As a second step, we do certain pre-processing operations on our review text. This is one of the movie reviews I randomly picked from our dataset. Over here, you may see we have these punctuation marks, special characters, HTML tags, and numbers. All of these add little to no value in telling whether a review is positive or negative. So we shall drop them all as part of this pre-processing step. I'll give you more insights on this when we get into the coding part. Moving on, our third step is word embedding, where we provision for converting our textual data to a numeric form using a very powerful feature extraction technique called word embedding. To use text data as input to a neural network model, we need to convert text to numbers first. There are popular techniques like one-hot encoding, which do a fair job in getting this done. However, unlike machine learning models, passing sparse vectors of huge sizes can greatly affect neural network models. Therefore, we need to convert our text to small, dense vectors, and this is where word embedding comes in. In the case of word embeddings, every word is represented as a n-dimensional dense vector. And the beauty of word embeddings is in the way it manages to retain the semantic relationship among words, as every token has n-dimensional parameters explaining its characteristics. For example, here we have these 4 tokens, man, women, king, and queen, along with their 7-dimensional vector representation depicting semantic relevance on a scale of -1 and 1. And these dimensions are nothing but a mathematical way to capture semantic relations among these tokens. Like this first dimension, we could have is living being, as all of these four tokens correspond to human beings. So we have these weights touching almost 1 for all of these tokens. And likewise for these remaining parameters as well. Just for visualization, word embeddings are like this huge nexus of words that have semantically similar words forming clusters, built with the help of a complex algorithm that establishes semantic relationships among words based on their usage in millions of sentences. So here we may see clusters of words that depict cities, travel, food, etc. And of course, the words in each of these clusters shall have similar n-dimensional vectors. In our case, we shall use the pre-trained GloveE word embedding with 100-dimensional vector for text to numeric transformation of our training data. Alright, coming back to our solution architecture, this next model training step is what sits at the heart of this entire exercise, where we shall train 3 separate neural network models, namely a simple neural net, a convolutional neural net, and a LSTM neural net, which are essentially 3 very popular but different approaches. Now let me give you a quick refresher on neural networks as well before we jump into the coding part of our project to execute this solution architecture we have been discussing. As one advances into the field of machine learning and neural networks, you would start appreciating more and more of how the human brain works. It's so intriguing how humans may learn new skills within a matter of days or months and be pro at it one day. Neural networks attempt to mimic the computation capabilities of our human brain. And that's the reason why these are quite suited to recognize numerical patterns contained in feature representations of real-world unstructured data like images, sound, text, time series, etc. Having said that, feature representations hold the key to train a powerful neural network. For image data, input pixels form the basis of derivation of these features. For sound, it's the time, amplitude, and frequency of the audio file. And in our specific use case, which is text data, it is the word tokens that form the user review sentences, forming the basis for derivation of features. After feature representation, the next important thing is to choose the neural network approach we may want to apply on our specific problem statement. Here we have prepared this crisp comparison chart for you to have a holistic idea on these different approaches. You may pause this video here if you wish to go through this detailed sheet at this point. If you may have any queries, post them in the comment section below and I'll be more than happy answering all of them. I'll use this moment to also introduce you to the problem of overfitting. Remember, as a child, many of us would cram up or memorize answers to complex mathematical problems and spit it out in the exam sheet. Neural networks also have a tendency to do so. It happens when the networks do not learn the general distribution of training data points and rather memorize the expected outcomes like this. Overfitting happens when the model returns high testing error as against a low training error. And if both error values are appropriately low and in close proximity, we have a well-fitting model. We shall observe this phenomena of overfitting during model training in our project. Alright, now it's time for us to jump into the coding part of our project and train our sentiment classification neural network models. So let's get coding. This is our Skillcate do-it-yourself toolkit for you. It has all these model related files including this training dataset, pre-trained GloveE word embeddings, this CSV with fresh IMDb reviews, along with their movie name and real IMDb rating, as you may see. Then this Jupyter notebook code file, and lastly this pre-trained LSTM model that we created previously. Let's open this Jupyter code file now to do a quick code walkthrough. In fact, I already have it open. Let's switch the tabs. Now we are here in Colab, we have segmented our entire code into these sections we see on the left side here. First one here we have is plan of action, which is pretty much self-explanatory by now. Let's move on to the second section, which is setting the environment. By the way, I ran this entire code file prior to recording this video to save on time. We'll take you through all the outputs anyway. Here, first up, we are mounting Google Drive to collab. Then we are setting our working directory to our project Toolkit folder within Google Drive. Post that, we are importing all essential libraries and functions with this next code cell. And that's it for setting up the environment. Next up, we have loading the dataset. Over here, first up, we are importing our IMDb movies dataset. Then for exploring our dataset, we are first checking for the shape. Then we are using this head function to actually see how our dataset looks. As you may see, we have two columns here, review and sentiment. As a good data science practice, we also check for null values, and we see there are none over here. Then we also check for data skewness across our data labels, and again we see there's no issues there as well. Next section is data pre-processing. Here in this first code cell, we are printing a review from our dataset. As you may see, we have punctuation marks, numbers, HTML tags, etc. over here. As part of pre-processing, we shall filter all of these out. Then we are defining this function called remove tags to actually replace HTML tags from the given reviews with white spaces. Next up, we are downloading the stop words from NLTK. And then we are defining this mighty pre-process text function that performs a series of operations on the input review. First one is this conversion of review text to lowercase, then replacement of HTML tags, punctuation marks, and numbers with white spaces. These single characters and multi-spaces are byproducts of operations conducted so far. So these are also dropped and replaced with white spaces. And finally, we drop stop words as well. And then the pre-processed review is returned as output of our function pre-process text. In this next cell, we are calling this pre-process text function on our reviews one at a time. Then we may have a look at the processed review in this next cell. In the next cell, we are converting our labels positive, negative to ones and zeros. And in the subsequent cell, we are splitting our dataset into 80-20 training test with this train test split function. In the next section, we are preparing our embedding layer. As a first step to this, we are using Tokenizer class from the Keras pre-processing text module to create a word-to-index dictionary. In the word-to-index dictionary, each word in the corpus is used as a key, while a corresponding unique index is used as the value of the key. Then we compute the vocabulary size, which is 92,394. What it essentially means is that our corpus has 92,394 unique words. Then next up, we are performing padding to set the length of all reviews to exactly 100 words. You can also try a different size. The list with size greater than 100 will be truncated to 100. For the list that have less than 100, we add zeros at the end of the list until it reaches the maximum length, which is 100 again. Post this, we are using GlowV embeddings to create our feature matrix For this, we first load the Glowy word embeddings and create a dictionary that will contain words as keys and their corresponding embeddings list as values. And finally, we create an embedding matrix where each row number will correspond to the index of the word in the corpus. The matrix will have 100 columns where each column will contain the Glowy word embedding for the words in our corpus. Calling this shape function on the embedding matrix, we may also check for its shape. As expected, we have exactly 92,394 rows, which is our vocabulary size, and 100 columns, which are the 100 Glowy dimensions. Alright, now we are at the model training step. First up, we are training a simple neural network. Over here, we create a sequential model. Then we create our embedding layer. The embedding layer will have an input of 100, which is the max length. The output vector dimension will also be 100. The vocabulary size is 92,394, as we know by now. And since we are not training our own embeddings and using the pre-trained Glowy embedding, we set trainable parameter to false. And in the weights attribute, we pass our own embedding matrix that we generated previously. The embedding layer is then added to our model. Next, since we are directly connecting our embedding layer to a densely connected layer, we flatten the embedding layer and then we add a dense layer with sigmoid activation function. Post that, we compile our model and then we start training. Once the training gets complete, then we compute predictions on the test set. Post that, we print model performance parameters. And finally, we plot model performance charts using this code snippet. As you may see, we get a test accuracy of 74.98%. Our training accuracy was 84.35%. This means that our model is overfitting on the training set. Overfitting occurs when the model performs better on the training set than the test set. Ideally, the performance difference between training and test sets should be minimum. Next up, we move to training a CNN model. CNN is a type of network that is primarily used for 2D data classification, such as images. A convolutional network tries to find specific features in an image in the first layer. In the next layers, the initially detected features are joined together to form bigger features. In this way, the whole image is detected. Convolutional neural networks have been found to do a fair job with text data as well. Though text data is one-dimensional, we can use 1D CNNs to extract features from our data. Talking about model architecture, here we are creating a simple CNN with one convolutional layer and one pooling layer. Code up to the creation of the embedding layer is the same as we have been using. Then we compile the model and start training. Once the training is over, we compute predictions on the test set, print model performance, and plot the charts. As you may see, our accuracy here is a good 85.79%, which is much better than the simple neural network results. However, our CNN model is still overfitting as there is a vast difference between the training and test accuracy. And finally, we come to the LSTM model training step. Recurrent neural network is a type of neural network that is proven to work well with sequence data. And since text is actually a sequence of words, a recurrent neural network is an automatic choice to solve text-related problems. In this section, we are using LSTM, which is a variant of RNN. Talking about model architecture, here after the same embedding layer that we have been using, we are creating an LSTM layer with 128 neurons. You can play around with the number of neurons, by the way, and rest of the code remains the same as is. Then we compile the model, then we train it, and once the training is over, we print model performance and plot charts the same way. Here we get the highest test accuracy of 86.43%, which is in very close proximity to the training accuracy of 87.12%. Even the charts show that the difference between the accuracy values for training and test sets is much smaller compared to the other two models. So with this, we may conclude that for our problem, RNN-based LSTM is the most suited approach for training a neural network. Guys, congratulations to you for making it to this point and training your own sentiment classification model using neural networks. You are the best. Now to finish things up here, we have this last section left where we make predictions on the fresh IMDb reviews for which we kept a test file in our toolkit. Over here, we are first loading this test reviews CSV. As you may see, it looks like this. Here we have the review text and the real IMDb rating captured in the CSV file. Then as usual, we pre-process our reviews text followed by tokenization and padding. And then we call our LSTM model on these reviews for predictions. Output of LSTM model is a number between 0 and 1, where 1 is positive sentiment. With this next cell, we are representing model results vis-a-vis our test file data. We are multiplying our model results with 10 so as to bring them on a scale of 0 to 10. And as you may see here, not only does our model predicts positive reviews as positive and negative reviews likewise, it also gives an insanely accurate prediction on the IMDb rating itself, which is mind-blowing, really. I would really encourage you to prepare your own such test file and run predictions using your trained LSTM model, just to further appreciate how cool this model is that we just trained. People, in case you have any questions on this project we discussed today, or you are preparing for a job interview or just need some career guidance in general, do set up a free one-on-one mentoring session with us by visiting our website skillcate.com to better your chances of getting hired with our expert advice. You may also write to us over email and WhatsApp. I hope you liked our work. Please subscribe to our channel now if you haven't so far. By the way, we have done a couple more sentiment analysis projects previously. This first one is basic sentiment analysis project where we use the traditional bag of words representation for feature extraction and naive Bayes estimator for binary classification. If you are just beginning your ML journey, I'll strongly recommend you to go through this project as well. The second project is built with scikit-learn pipeline using TF-IDF Tokenizer for feature extraction and support vector machine for classification. sklearn pipeline, by the way, is a low-code magical way of building ML models, so do check this out as well if you are curious already. And this third project is on how to deploy a sentiment analysis project in a live environment and performing live queries. This for sure is the coolest among the three projects we have here. Link to all of these is in the description part below. I would highly recommend you to go through these projects as well to further strengthen your understanding of sentiment classification problem and having a complete end-to-end visibility of solving a machine learning project. We launch new machine learning projects every week, so to get regular updates on our ML projects, do subscribe to our channel and recommend us to your friends as well, so they may also benefit from our work. Thanks for all your support. Keep learning. Bye.